Now that we reviewed the basics of deep networks, we want to turn to discuss how we can harness their power in the context of wireless communications and see how they can help us solve difficult problems in the context of 5G and beyond networks. Let's begin by considering why we may need machine learning in the context of communications. In general, we know that when treating various design problems in communication systems, we often end up with complicated optimization problems, which can include many design variables. They may be non-convex or even untractable, and often depend on system parameters that might not be known. For example, one of the fundamental problems in the physical layer is designing an optimal receiver to detect and decode transmitted symbols. This often leads to combinatorial optimization problems and also requires knowledge of the physical channel. Now, the channel is often estimated in advance, for example, using pilot symbols, but this necessitates additional bandwidth and capacity. It requires time, and it assumes that the channel doesn't vary too quickly, which is not always practical, for example, in a multi-user environment with rapidly changing channels. In this case, estimating the channel repeatedly between all users is not going to be very practical and is going to consume too many channel resources. Another good example is multiple antenna systems, where there are many design issues related to beamforming in both the transmitter and the receiver sides, which again lead to various combinatorial problems, especially when we consider antenna selection methods, and they again will require knowledge of the channel statistics. Security and coding issues are another area where optimization is necessary and often quite complicated. On higher levels of the communication system, we again tend to end up with various optimization problems, which will involve multiple users, often discrete variables, and require knowledge of many system parameters that are not often known, such as channel gains, number of active users, user codes, timing constraints, and many more parameters. To get a better sense of where machine learning can help in communication and why it is needed, let's take a closer look at one of the most basic operations of a communication system, which is symbol detection. So in a standard detection problem, we're going to have a transmitter that wants to transmit messages or symbols to a receiver over a given channel, in our case illustrated over here, a MIMO channel. Now the transmitter is going to do that by sending a signal S, which we're going to obtain as an output Y. In order to recover S from Y, we're going to rely on a model that describes the relationship between Y and S, where the most popular model is the linear Gaussian model, in which the received signal is assumed to be a linear combination of the transmitted symbols over a block plus a Gaussian noise. Now this model is used really due to its simplicity. Under this model, there are very many well-known receivers that are optimal for different criteria. For example, we could design a detector that maximizes the likelihood of the received output Y. However, in practice, the channel may not be linear, the noise may not be Gaussian, and most importantly, the channel is often not even known, and as we alluded to already, estimating it repeatedly is going to consume too many channel resources. So this seems to be a good problem to examine and ask whether using the tools of machine learning, we can avoid knowing the channel and having to model it exactly. In general, we know that machine learning provides methods that do not require not knowing the exact model. So this seems like a very relevant area in which to apply machine learning tools. So how would we do that? Well, a straightforward idea is to just take this current receiver and replace it by a deep network that uses end-to-end training to perform the detection. However, the difficulty is that the advantages of machine learning typically come into play when we have very large training sets, which will not typically be the case in a communication environment that is rapidly changing. In such a setting, it will be impractical to collect large training sets every time the channel changes. Furthermore, as we know, in general, although machine learning methods can work very well, very little is known about their optimality properties and the quality of the solutions from a statistical perspective. On the other hand, standard communication theory provides us with methods that are optimal under various criteria and for which we can analyze the properties of the solution in a convenient manner. So this raises the interesting question of whether, instead of using black box machine learning solutions that were not designed specifically for communication problems, we can combine machine learning and communication in a way that preserves some of the desirable properties of the standard communication solutions. In other words, what we'd really like is to develop learning methods that rely on well-understood models of communication systems rather than generic solutions. In contrast to deep networks, signal processing and communication are in general based on physical models. This allows us to easily incorporate domain knowledge and structure into the methods. It also allows us to perform inference with small data sets and to easily assess the quality of the output. The main drawback, however, of traditional signal processing methods is that they rely on accurate model knowledge that we already spoke about in the context of communication. And in addition, inference can often be quite slow and difficult to implement. Therefore, the question is whether we can combine the ideas of models with deep learning in order to be able to arrive at compact, interpretable, and simple to train data-driven systems. To see how we can do this, let's take a bird's-eye view on model-based processing versus deep learning. In a standard model-based method, we usually have some set of measurements y, from which we want to infer some unknown x. So in the communication context, y was our received signal and x were the symbols we want to infer. We typically also have a model that relates y and x, and we use that to design an algorithm that determines x by optimizing some metric, which relies on this measurement and the known relationship. So here in this example, the relationship is y equals approximately g of x, and f is going to be a metric that we're going to want to optimize. When we go ahead and try to optimize f, we typically end up with a series of steps that need to be carried out in an iterative fashion. So we typically have some generic mathematical operation, and we then have a set of iterations between a generic computation and some block that depends on the underlying model. And then we typically have some mathematical operation at the end, which will give us the desired outcome, x. Now, on the other hand, in deep learning, we do not assume we have a model, but instead, in some sense, we're going to perform magic in a sense that we're going to replace the model by a black box that does not know anything about the problem. Instead, it's going to obtain lots of inputs and outputs that are paired, and from then it's going to learn the parameters of a network in a series of layers that form the desired deep network. Once we get the deep network, we're going to apply this to a new input y and obtain the desired recovery x. So the question is how we could combine these two approaches, and to do that, we're going to suggest two different methods. The first is to integrate model-based methods into deep learning by relying on the idea of unfolding that was first suggested by Gregor and LeCun. The second approach we're going to use is the reverse in some sense. So we're going to integrate deep networks into existing model-based algorithms. Okay, so what we're going to do next is just briefly describe these two approaches, and then Nir is going to take over and show how both of these approaches are actually used in the context of different communication problems. So let's begin by looking at unfolding, which was first suggested by Gregor and LeCun and has gained growing interest in both the signal processing community and the wireless communication community. So the basic idea in unfolding is to take our optimization problem that we talked about before, and instead of just looking at the loop of iterative steps, we're going to explicitly write out several of these steps. So for example, we could explicitly write out 10 iterations. So until now, we didn't do anything new. We're basically just implementing an iterative algorithm. But the learning is going to come into play in the final step, where instead of implementing these iterative steps that are typically going to depend on channel parameters that we don't assume are known, we're now going to use training data to learn the parameters in each of these steps. So in this way, instead of getting a generic deep network, we're going to get a network where we have a small number of layers, and the structure of these layers follow from the optimization problem. But instead of plugging in channel parameters that might not be known, we're going to learn them from training data. So this is the general approach behind unfolding that was applied to many different problems in signal and image processing. And we have a recent review where we discuss different applications. It has also become very popular in communication networks, and we refer here to a review specifically for communication, and we'll see a few examples in a couple of slides. So this is the first approach we can use in order to use a model-based approach in the context of communication. The second approach we suggest is very different. So it's actually starting from the given solution. So starting from the generic solution that we know is good when we know the channel parameters, and then just taking the block that depends on those unknown parameters and replacing it with a generic deep network. But now this deep network is only going to be replacing a specific block, not the end-to-end solution, and therefore we still retain the structure of the well-known communication solution, but do not require knowledge of unknown parameters, which are estimated by this deep network. So this again was reviewed in a recent paper that we wrote that reviews this approach, and we're going to be talking a lot about it in the next few slides. So what we're going to do next is see how we can use these two approaches, the unfolding approach and this data-driven hybrid approach, and apply them to various different communication problems.
In this part of the tutorial, we will present some applications of deep learning in receiver design. Specifically, we will focus on the problem of symbol detection, where we have a set of channel inputs which are symbols taken values in some discrete constellation. They go through a channel and the receiver observes its channel output, from which its task is to recover the transmitted symbols, and to that aim, it utilizes deep learning techniques. We will consider three main approaches with concrete examples for deep receiver design. We will begin with the usage of established deep networks for this task. Namely, we're using a conventional neural network architecture in order to classify or to infer the symbols from the channel output. As an example, we will show the sliding bidirectional recursive neural network, which was proposed as a symbol detector designed for finite memory channels. Then we will discuss how unfolding can facilitate symbol detection using deep networks. And as an example, we will show DetNet, which was proposed as a symbol detector, unfolding-based symbol detector for MIMO channels. Then we will go into data-driven hybrid algorithms advocated earlier, showing several concrete examples: the implementation of the Viterbi algorithm in a data-driven fashion, the implementation of the BCJR algorithm, and DeepSeek, which implements soft interference cancellation for MIMO detection. Let us begin with the usage of symbol detection using established networks. So the rationale here is to replace the receiver with a conventional neural network architecture, acknowledging the fact that symbol detection is essentially a classification task. We're trying to recover a block of symbols taking values in discrete set from a channel output which may take values in continuous set. So the rationale here is to identify what deep architecture is suitable for the considered channel, which deep architecture can carry out symbol detection reliably for the considered case. Once we identify this architecture, we just need to use it as symbol detector and simply train the whole thing in an end-to-end manner. And hopefully, by showing this deep architecture a sufficient amount of labeled pairs of channel outputs and the corresponding symbol, the resulting deep symbol detector should be able to carry out inference reliably. As an example, let us consider a finite memory channel in which the channel output is some function, stochastic function, unknown function, of its last set of, let's denote by L, channel inputs. So this is a conventional finite memory channel, though notice here it doesn't have to be linear. In the work of Farsad and Goldsmith from 2018, they proposed to use an architecture which is based on bidirectional recursive neural network. And the rationale here stems from the fact that the maximum posteriori probability detector for such channels actually implements a set of forward recursion and a backward recursion in order to recover its corresponding symbols. Now, I will specifically go into those forward recursion and backward recursion later on when we speak about the BCJR algorithm. But let us at this point just say that the implementation of two-directional recursions which meet at each specific symbol allows one to implement the maximum posteriori probability symbol detector, which is a symbol detector which minimizes the error probability. So in light of that knowledge, that's for these kind of channels, the best thing to do is some forward and backward recursions. What Farsad and Goldsmith propose to do is just to learn those recursion using bidirectional recursive neural networks. And this essentially exploits the temporal correlation in the observed channel outputs. And once we do that, it allows us to exploit the channel memory without doing it explicitly. We're just utilizing a neural network architecture which is capable of exploiting temporal correlation in time sequences. In their work, they trained it over multiple channels, only once, but they did use the order of 30 million training samples in order to train this highly parameterized neural network. And what they were able to show is that for some scenarios, the resulting receiver comes quite close to the performance of the maximum likelihood sequence detector. There are several drawbacks of utilizing deep conventional architectures for symbol detection, and the most notable one stems from the fact that we're now having a very highly parameterized network with a very large number of tunable parameters, implying that you need very large training sets. In the end of the day, in the work of Farsad and Goldsmith, they used about 30 million training samples, and we know that communication channels are dynamic. So even if you train it over a set of channels, at some point the channel may change in time and you may have to retrain the whole thing, which takes considerable amount of time. Also, by using just a conventional, some sort of a black box architecture, we end up with a receiver which is quite non-interpretable. The main advantages of using this approach stems mostly from its model invariance. It does not need to impose a specific relationship between the channel output and the channel input. It does not need to know its parameters, and it is also applicable in very complex setups. For example, in the work of Farsad and Goldsmith, they were able to apply their SBRNN-based symbol detector to very complex channels like molecular communication channels and channels in which the input-output relationship cannot be expressed analytically, but is known to obey a finite memory structure. For the unfolding case, here the rationale is somewhat different. Here, instead of trying to identify what network architecture would do the symbol detection task better, we're trying to identify an iterative optimization algorithm which is suitable for the task of symbol detection under the considered channel model. And then we fix the number of iterations and unfold each iteration into layers, just like we have here in this architecture. And once we've done that, we end up with a deep neural network which imitates the operation of the iterative algorithm, and we just train the whole thing in an end-to-end manner, again, hopefully, by showing this deep architecture a sufficient number of labeled samples, namely a pairs of channel outputs and the corresponding symbols, the resulting architecture should be able to carry out this optimization algorithm reliably. Let's see an example. The example we will discuss here is the one by the work of Samuel Diskin and Wiesel, Learning to Detect. This architecture is called DetNet, and it's suitable for linear MIMO channels in which the channel output is given by some metrics times the channel input plus noise. Specifically, they consider the case where the channel inputs are BPSK symbols and the channel matrix is known. So note that we're already beginning with a case in which we know the model and we know the parameters. Now, the goal here, assuming that the noise is Gaussian and IID, we know that the maximum likelihood sequence detector is simply the one which finds the minimum distance symbols, and it boils down to this optimization algorithm in which we're trying to recover the symbol vector which after applying the channel to it, will be the closest to our observed channel outputs. Unfortunately, when the dimensions of S are large, namely we have a large number of transmit antennas or a large number of transmitters, this optimization problem becomes computationally infeasible, as the set over which we are carrying out our search grows exponentially with the dimensionality of this vector S. Therefore, what one could do in order to tackle this problem, which is challenging, especially when the dimensions are large, is to utilize projected gradient descent. Projected gradient descent means that we're looking at this problem here, only the minimization of the distance, and this one can be tackled using gradient descent, which is given just here. Okay, so here we're taking, like at each step, we're taking our current estimate, we're reducing from it the gradient with respect to the symbols times the step size. Here eta t is the step size, and this pi here represents the projection, because these values of st cannot take any arbitrary value, they have to be in the set of plus minus 1 to take discrete values. So this is why we need this projection operator, and by taking the gradient explicitly we obtain this expression here, and this is exactly the projected gradient descent algorithm for solving this problem here. Now, how do you unfold it? Let us look again at this expression. And as we can see, there's the expression here in blue, which is the conventional gradient descent, and the expression in red, which is the projection. And then we can replace each one of those with a dedicated layer which imitates this approach. So there's the operation in blue is exactly what we see here. This looks like the each step of gradient descent, in which instead of having a step size, we have those parameters delta, which are learned. And we're just taking this operation, which looks like gradient descent, and we're applying some conventional layer of a neural network to it. It's just some affine transformation followed by ReLU activation. So this value here, z of t, is exactly as if we taken our previous estimate and apply gradient descent and some layer of a neural network to it. And then this projection, which since we're projecting it to either plus or minus 1, but we want to be able to propagate to it, so we're taking some soft approximation of this hard projection, and it can be replaced with this sigmoid function, where sigmoid resembles the projection into plus minus 1, it resembles a sine function. But instead of applying it just to this output, we're also adding another linear layer here in the middle. So we can look at it as if each one of those pairs is one iteration. It consists of two layers of a neural network. One, which is the layer here in blue, which is supposed to imitate the gradient descent step, and the layer here in red supposed to learn to carry out the projection step. And by adding a sufficient number of layers, we're actually obtaining a neural network, a deep neural network, in which the input to the overall network is y, the observation. The input of each layer to the tth layer is this previous estimate of the previous estimate from the last iteration, and its output is the current estimate. And as we can see, there's like some sort of skip connections because the input was also provided to each one of those layers. And we also need to know the channel, which appears here. And by doing that, well, first, we have utilized knowledge of the channel. We end up with a relatively large network. What they have done in their paper, they train it with using about 250 million samples, where the largest channel condition they were tackling is the one, if I recall correctly, it had 60 different transmitters, which is a very large channel, very combinatorically difficult task. Now, again, we're boiling down to the problem here that we end up with a very large network, a very large number of parameters to train. And although those parameters are inspired by an optimization algorithm, we do need a very large training set to train it. And we are, if the channel starts changing, we'll need probably to retrain the whole network. Also, specifically here for that net, we actually need to know the channel. We need to know its model and its parameters. So in the end of the day, the main benefit here over conventional algorithms, like actually implementing projected gradient descent, is mostly in inference speed. Namely, we don't have to actually carry out all those iterations. Doing it over a deep network is much faster than just doing the iterative process analytically. But on the other hand, we do need to waste a good deal of time and a good deal of computations in training this network. Now let us go to data-driven hybrid algorithms, in which the rationale is somewhat different compared to our previous approaches, which just used a deep network, either a conventional architecture or an unfolded one to carry out the complete symbol detection task. Here the rationale is to select a symbol detection algorithm which is suitable for this specific channel and this specific problem, and to identify which of its computation requires knowledge of the underlying model. Then we replace those computations with dedicated and relatively compact networks, and we don't train the whole thing in an end-to-end manner. We're just training those dedicated components such that we can implement the overall algorithm in a data-driven fashion. As a first example of a data-driven hybrid algorithm, we shall consider the Viterbi algorithm. Viterbi algorithm is one of the main symbol detection algorithms. It's a fundamental tool in digital communication, and it can be considered to implement the maximum likelihood sequence detector for channels obeying this Markovian structure, in which the conditional distribution of the block of channel output given the block of inputs can be decomposed into the conditional distribution of each channel output given a set of L previous channel inputs. So it's exactly a finite memory channel, just like we considered for the sliding bidirectional recursive neural network case. And what Viterbi proposed to do in his algorithm proposed in the late 60s is to model each set of symbols which could have led to a single channel output as a state in a state machine, and then essentially do dynamic programming over it, which we will elaborate on next. This obviously worked very well. Viterbi ended up co-founding Qualcomm. Here is receiving the Medal of Science from George W. Bush. And to understand how this algorithm works, let us do it in a heuristic graphical manner, which captures the essence of Viterbi algorithm. So we have a finite memory channel. Namely, we have a channel in which the channel input at each given time only depends on its L channel input, on its L transmitted symbols. And in this specific example, we'll consider just memory of size 2, namely each channel output depends only on the current channel input and the previous one. And we're essentially building upon the fact that because it's a Markovian conditional distribution, we can factorize the log likelihood as the sum of corresponding log likelihoods. And then what we essentially do is, instead of computing this quantity here, we compute the quantity on the right using dynamic programming. And what does it look like? Let's say we have this channel output now, denoted Y1. We take this channel output and we're computing the log likelihood, the negative log likelihood, for each possible symbol combination which could have led to this corresponding channel output. And we're adding this to this graphical form. And here we're computing these costs for each specific combination of channel inputs which could have led to that specific channel output. And then the next thing we do is we update this path along this resulting diagram, which is what's called the trellis diagram. Then we take the second channel output. We again compute the log likelihood for each possible state combination which could have led to that. And then again, we're continuing by maintaining those overall paths where we sum the log likelihoods along each path. Again, another channel output comes in. We're again computing the costs, but then at some point we would start having conflicts, and we'd start having several paths leading to the same state. And what we do here, we only maintain the minimal path, the path with the minimal loss along it, which essentially boils down to dynamic programming. And once we do that, at some point we would have a state for a given time instance, only a single state has a legitimate path leading to it. And then we can use this specific state for decoding. Then we can actually know what was the symbol which was transmitted, in this case, 2 time instances after each symbol we're receiving. So this is why it operates in pseudo real time, namely it has some delay, which is dictated by the memory of the channel. And we do this all over again and again. This is actually how it operates. And what we see here is that, well, there are 2 things that happen. First, due to the optimality principle of dynamic programming, we're actually able to compute the negative log likelihood here to minimize it, which means that we're essentially implementing the maximum likelihood sequence detection. And since on each channel input, we're computing the exact same number of log likelihoods, the complexity only grows linear with the block size. And we saw that it operates on pseudo real time, namely there's only a small delay here. Let us now observe the Viterbi algorithm and take a high level perspective of it, and note that the only part of the Viterbi algorithm which requires prior knowledge of the underlying channel, namely the conditional distribution of the channel output given its input, is in the likelihood computation. Once we compute the likelihoods, the rest of Viterbi processing, which accounts for the temporal correlation, for the finite memory of the channel, is essentially dynamic programming. It's just a set of algebraic manipulations. This allows us to implement Viterbi algorithm in a data-driven manner by simply learning to compute the log likelihoods. Here, which is what we call ViterbiNet, we replace the likelihood computation, which are model-based, with learned likelihood computations. And once we do that, assuming that we have an accurate estimate of those likelihoods, we can actually implement Viterbi algorithm in a data-driven fashion by learning only what has to be needed for Viterbi. Now, we note that, for example, if the channel is stationary, then this mapping of the channel input into a set of log likelihood values does not depend on the time index. There's only one function which has to be learned. So how do we learn it? Well, there are actually two different approaches to do that. First is to use classification networks. Namely, we first use a classification network to compute the conditional distribution of the symbols of the channel input given the observed channel output, and then we convert them to the desired quantity, which is the conditional distribution of the output given the set of inputs which could have led to that, where the Markovian structure of the channel is encapsulated. It can be inferred from the previous quantity using Bayes' theorem. Alternatively, we can also use regression networks. Namely, we can assume some given conditional distribution of the input given the set of the channel output given the set of channel inputs, which is what we're interested in. We can assume that it is only dictated by its first and second order statistical moments and only estimate them. So how do those architectures look like? Well, for the classification network, let's know that it consists of two components. The first component is this classification network whose input is the channel output, and its task is to recover the set of channel inputs, the set of symbols which could have led to this channel output. Now, since it's a classification network, it's trained to minimize the cross entropy loss. It has a softmax output layer. Then essentially what we learn here is the conditional distribution of each possible pair, of each possible combination of channel inputs given that channel output. And now let us recall that classification networks are capable of accurately learning the conditional distribution of a cat given an image, which is way more complicated than learning the conditional distribution of a set of constellation symbols given an observed channel output. So this implies that we can use a relatively compact network here in order to implement this part. However, what we are interested in is not the conditional distribution of the channel inputs given the channel output, but the opposite. So what we can do is use another machine learning tool to learn the marginal PDF, the marginal probability density function of the channel output. And we can build upon the fact that, for example, we know that the input is discrete, so the marginal distribution of Y has to obey some finite mixture model. And so we can use some sort of kernel density estimation, like a finite mixture model PDF estimator, to estimate it reliably using, for example, some expectation optimization algorithm, and then combine those two quantities using Bayes' rule to obtain a hopefully accurate parametric estimate of the channel output, the conditional distribution of the channel output given each possible combination of channel inputs which could have led to that, which is exactly the quantity we need for Viterbi algorithm. These are the values assigned to each one of those cost values along the trellis diagram. Alternatively, we can also use regression networks. Namely here, our input to the network is the combination of channel inputs, namely the state. And the output are the estimated first and second order statistical moments of the channel output given those pairs. So this does not explicitly estimate the conditional distribution. It estimates the first and second order statistical moments of this conditional distribution. And then once we have these quantities, we can just estimate the conditional distribution as Gaussian. Now, the question is, how do you train a regression network to learn the mean and variance of conditional distribution? Well, there are two approaches to do that. The first is to minimize the objective, which can be treated as the negative log likelihood, assuming that it's a Gaussian conditional distribution. So this is exactly the negative log likelihood. It's one possible way to do it. Alternatively, we can just look at this mean value as an MSE estimate of the observation and the covariance matrix as an MSE estimate of the empirical covariance. Here, it's not the covariance, it's the empirical second order statistical moment, but these are two methods using which one can implement a regression network to learn the first and second order statistical moments of the conditional distribution of the channel output given a combination of channel inputs which could have led to that. Now, both approaches which we have discussed, the one uses classification and the one uses regression networks, provide a parametric estimate of the conditional distribution of the channel output given each possible set of channel inputs. Using that, we can implement Viterbi in a data-driven manner. And does it work? Well, let us see for this numerical example here. Now, here we're considering a network which is trained with merely 5,000 symbols. Let us recall that the previous examples we discussed were trained using the orders of several millions of training symbols. And what we have here, the curve in blue, is the performance of the Viterbi algorithm, which knows the channel at each given time instance. And the curve in red is the performance of ViтерbiNet. And as you can see, it essentially coincides with Viterbi algorithm when trained using a very, very small number of training symbols. Now, we can also see that the curve here in purple, this is the SBRNN receiver we discussed earlier, through the trained using the same number of training samples. So as you can see, the performance gap is not that big, but still, the ViтерbiNet algorithm actually approaches the performance of its model-based counterpart since it is designed to do so. Now, another advantage of going into machine learning-based methods is that you obtain improved robustness to uncertainty. What do we mean by that? Now, if we implement model-based Viterbi, but we do not know the channel exactly, we have some error, then the performance deteriorates significantly. This is the black curve here. Now, also the SBRNN, if it's trained on a set of channels, each one with slightly different statistical characteristics, meaning that we did not know in advance to exactly which channel we will be tested in during inference, then the performance significantly deteriorates when we're using a relatively small number of training symbols. However, the green curve here, this is ViтерbiNet trained using the same level of uncertainty, namely over a variety of different channel conditions. And as we can see, it actually obtains a performance which is very close to as if it was trained using the exact same channel conditions over which it is tested. Namely, by using machine learning tools, embedding it into a symbol detection algorithms, we're able to robustify it. We're not only able to approach its optimal performance, namely we're approaching a maximum likelihood sequence detection using a relatively small number of training sets, we're also improving robustness to uncertainty. Now let us proceed to another form of symbol detection based on graphical models. And if we started with the Viterbi algorithm, let us continue to what's called factor graph methods. Now, a factor graph methods are a family of signal processing algorithms which are based on the ability to represent distribution at a graph, and then they carry out inference using message passing over the graph, exploiting the graphical model to implement this with reduced complexity. Okay, so this sounds like very high level, but let's understand how does this work. Okay, so to that aim, let's go back to our finite memory channel, in which the conditional distribution of a block of channel outputs given its corresponding channel inputs can be factorized using this Markovian structure. Okay, So what we do here, we define a state vector, which is a set of channel inputs which could have led to the, which are statistically related with the given channel output, the given observation. And then we can write the joint distribution of this block of channel output and the block of channel input using this factorization. And what we do, we call this function here the function node, and the variables inside it we call the variable edges, and then we obtain this graphical representation which encapsulates the joint distribution of the channel output and the channel input. Now, this graphical representation allows us to carry out inference with relatively low complexity. And in order to do that, we will go into what's called the sum product algorithm, or specifically its special case for these kinds of joint distribution, which is what's called the BCJR algorithm. So in order to do that, let's understand how can this graphical model facilitate the computation of marginal distributions. Let us look at the marginal distribution, marginal joint distribution of the channel output and two consecutive states. Now we know that this joint distribution using the law of total probability can be obtained by summing over the overall joint distribution. Now let us write this overall joint distribution using its factorization, where these are the function nodes and these are the variable edges. And then we can actually write this as the function node which is relevant to the current two states which we are observing, as well as this term here which we will call the forward message, as well as this term here which we will call the backward message. And actually we've managed to factorize this condition, this marginal distribution, into a product of three components, in which the forward message can be actually computed recursively because we can write it down explicitly, and again exploit this Markovian structure to see that it can also be obtained directly from the forward message with respect to the previous state. Now the same goes for the backward message. Now this term here can also be factorized as follows, and we can also obtain it in a recursive manner from the backward message of the next state. So if we now look over the factor graph, this graphical representation of the joint distribution, we can actually see that if we want to compute the marginal distribution of states S3 and S2, as well as the overall block, observed block of channel output, all we need are the backward messages along the graph to here, the forward messages along the graph here, where each can be computed recursively, and the value of the function node here. Now, by computing this marginal distribution, we can actually implement what's called the BCJR algorithm, proposed back in '74, which first computes those marginals by message passing over the factor graph, which is what we just explained, and then use them to compute the maxima posteriori probability by simply doing maximization with respect to the specific state, which we are, with respect to a specific symbol, which we are interested in. So what this computation allows us to do, it allows us to compute this marginal distribution in a linear complexity due to its recursive manner. And then we can use this quantity to evaluate the maxima posteriori probability symbol detector for each given symbol. Namely, we're actually implementing here the optimal symbol detector in the sense of minimal error rate. Okay, so this is the BCJR algorithm. Now let us note that all we needed in order to carry it out was knowledge of the factor graph. So if we were to know the factor graph, namely we were to know the function nodes, we could have carried out the message passing over the learned graph. So what we are proposed to do here, what we call BCJRNet, is essentially to learn the factor graph and then do message passing over the learned graph. This is based on our previous knowledge that the channel obeys this Markovian structure. Once we know that, all we have to do is learn those function nodes. And once they are learned, we know the graph. Now, how do you learn them? Okay, so let us note that for a finite memory channel, those function nodes, which are what we are interested in, can be written as the product of the conditional distribution of the channel output given its corresponding state times the conditional distribution of the corresponding state given the previous state. That just follows from the Markovian structure. Now, we know that this term here is typically known, right? Because it's the conditional distribution that a set of symbols were transmitted given the previous set of symbols. So it usually obeys some sort of a uniform distribution if one is a shifted version of the other. So this can assume to be known. It typically is known. The other quantity, which is unknown, which actually depends on the channel, we can note that it is exactly the same quantity which we learned in Viterbinet, which means that we can learn those function nodes using the same architecture we used for Viterbinet. And again, if the channel is stationary, it means that those function nodes are exactly the same function throughout the complete block. So we only need to learn one function node. We only need to train one of those neural networks to learn this conditional distribution and combine it with our knowledge of the condition of the transition distribution and our knowledge of how the BCJR algorithm operates over the factor graph, where instead of using the model-based factor graph, we're using the one which we learn. And that is what we call BCJRNet. We're applying BCJR of the learned graph, and assuming we have an accurate estimate of the function nodes, we actually implement map symbol detection. This actually was just recently published in ISIT. It is also available on arXiv, this paper. So how does it work? Well, actually, by doing so, we don't need a lot of training symbols here. Notice these are 10K symbols. Again, please recall that for previously proposed deep detectors, one had to use the order of 10 million, 100 million training samples. Here, we're talking about 10,000 training samples. And by doing so, we're actually able to implement the BCJR algorithm. So the red curve, which we don't really see, is the data-driven BCJR algorithm, and the blue curve is the learned one. So we are actually able to learn the factor graph accurately and obtain the exact map maxima posteriori probability symbol detection as the model-based BCJR. Again, we also see that by utilizing machine learning, we're improving robustness to uncertainty. Because if we have some level of uncertainty in our knowledge of the channel, we have inaccurate function nodes in the factor graph, and the model-based BCJR algorithm deteriorates. However, under the same level of uncertainty, the data-driven implementation, namely when it is trained over a variety of channels, because we do not know in advance exactly to which channel it is applied, but it's in the same order of uncertainty as the order of under which we have tested the BCJR algorithm here, we're actually able to learn the function nodes quite accurately and obtain roughly the same performance as if we had trained the function nodes over the exact same channel conditions under which it is tested. So we're actually here able to learn optimal symbol detection. We're able to learn the maximum posteriori probability symbol detection from data by learning the factor graph and building upon this learned factor graph to implement the algorithm which we know is suitable for such channels, which is the BCJR algorithm. Before we go further, let us do some brief comparison between Viterbi and BCJR, which are the two algorithms we've considered as symbol detection over finite memory channels. Now let us recall that first, what Viterbi does, it computes the maximum likelihood sequence detector, while the BCJR learns the map symbol detector. So the BCJR actually minimizes the error rate for each given symbol. Now, the complexity of both algorithms grows linearly with the block length, but it does grow exponentially whereas the number of states or the channel memory or the cardinality of the channel inputs, the constellation size. So once these grow large, either the cardinality of the input or the memory, both algorithms will become very computationally complex, but it should be noted that typically BCJR is more computationally complex than Viterbi, even though they both grow linearly with the block length. BCJR requires those two-directional recursion, while Viterbi only implements a one-directional recursion, only the forward path. Viterbi, due to the fact that it only computes the forward path, is able to operate in real time with some delay, which is dictated by the memory, while BCJR requires the complete block to be received before it can detect it. And both give rise to a data-driven implementation. One is Viterbinet, and the other is BCJRNet, which utilize relatively small training set in order to learn to carry out those model-based algorithms. So far, we have considered the application of data-driven hybrid algorithms for the family of finite memory channels. This was done by identifying the proper symbol detection algorithms, either the Viterbi algorithm or the BCJR algorithm, and replacing their model-based computations with dedicated machine learning methods. By doing so, we ended up with a data-driven implementation of the model-based algorithm. Let us now proceed to a different family of channels, to MIMO channels without memory. Here, the cardinality of the measurements, which is dictated by the number of antennas, can be very large. Also, the cardinality of the inputs, which is dictated by the number of transmitters, can also be very large. As a result, the algorithms we've considered earlier, the BCGR algorithm, the Viterbi algorithm, are simply not feasible here, regardless of whether they're implemented in a data-driven fashion or in a model-based fashion, because the complexity grows exponential with the cardinality of the input. This gives rise to the question, which symbol detection algorithm one should use and can be implemented in a data-driven fashion for MIMO detection. To that aim, let us look at two extreme cases, which are separate decoding and joint decoding. Joint decoding is the optimal approach. It means that we're taking the channel output and we're simultaneously trying to recover the combination of channel inputs which could have led to that specific channel output. For example, if we look at a linear channel with Gaussian noise, like we did in the derivation of DetNet earlier, the resulting problem boils down to this optimization, which is carried out over a set whose cardinality grows exponentially with the number of transmitters. Hence, it becomes unbearably complex when the number of users is very large. Alternatively, the dominant approach currently in the massive MIMO literature is to implement separate decoding. Separate decoding means that we're using the channel output to decode the symbol of each user separately while treating the remaining symbols as noise. For example, if we go again to a linear MIMO channel, a Gaussian channel, this can be carried out by taking the channel output, applying some linear filter to it, and trying to recover the corresponding symbol from the output of that linear filter. As a result, the complexity here only grows linearly with the number of users. However, its performance is strictly suboptimal, and in one of our recent works, we actually characterized how suboptimal is separate decoding in the massive MIMO regime. There is another approach which combines separate and joint decoding, and this is the family of interference cancellation methods. Interference cancellation methods decode the symbol of each user separately. However, in each such decoding, previous decoding of the remaining symbols, namely the interference, is used to facilitate the recovery. By doing so, operating in such an iterative fashion, one can obtain some balance between performance, approach the performance of joint decoding, and complexity, namely maintain a complexity which only grows linearly with the number of transmitters, like in separate decoding. Specifically, the iterative interference cancellation method is based on implementing separate decoding multiple times while utilizing the decoded symbols in the previous iteration to facilitate recovery in the current iteration. There's also the problem here of error propagation, and if we have decoded one symbol incorrectly, it may influence our ability to recover the remaining symbols, and that motivated the derivation of a soft interference cancellation method. Was derived about 20 years ago, and here, instead of estimating the symbols in each iteration, we're estimating a conditional distribution, which to facilitate the estimation of the remaining symbols in the next iteration. So this looks like the block diagram we have here. We have the channel output. We're doing interference cancellation and recovering an estimate of the soft symbol at each iteration. And then we're using those soft symbols to cancel the interference in the subsequent iterations. Going into further details, the soft iterative interference cancellation algorithm considers the symbol detection over linear Gaussian MIMO channels of the following form, in which the channel vectors denoted H1 to Hk are known. And then it operates in an iterative fashion, where on each iteration index Q, it implements a mechanism for canceling the interference and estimating distribution of each symbol of index K using the channel output and the estimated interference from the previous iterations. In particular, the interference cancellation block, marked here, takes the channel output, provides an estimate of the interference using the mean values, and then just cancel the interference by subtraction, as we see in this expression here. And furthermore, the conditional distribution estimates from the previous iterations are also used to provide an estimate of the soft symbols. How is that done? We're taking the interference canceled channel output, and we're assuming that its distribution, given the current symbol, obeys a Gaussian distribution with some mean value, which is dictated by the current symbol and the channel vector, but also the variance here is determined by the variance of the noise plus the estimated variance of the remaining symbols computed from this conditional distribution estimate. By doing that, we essentially model the interference as noise with a known variance and mean. By doing so, we can now obtain an estimate of the conditional distribution of the desired symbol given the interference cancelled output from this Gaussian distribution via Bayes theorem. The soft iterative interference cancellation detector depicted here is highly model dependent. Its model dependence is reflected in several parts of the algorithm. First, it assumes a simplified channel model in which the interference can be cancelled by subtraction. Namely, the channel has to be linear, in which the effect of the interference is additive. Furthermore, the channel noise has to be Gaussian. Not only Gaussian, it has to be white Gaussian. And the channel parameters, namely the channel vectors, must be accurately known as they are repeatedly used throughout the algorithm. Now, if you have some uncertainty, the performance is expected to deteriorate, motivating us to look into channel model independent implementation, a data-driven implementation of soft iterative interference cancellation by integrating machine learning methods. This work, which is called DeepSeek, is actually presented later on this week here in ICASSP, and it begins by considering the soft iterative interference cancellation detector, identifying its basic building blocks, which operate on the postulated conditional distribution of the interference and the channel output, and they produce an estimate of the distribution of the corresponding symbol. As such, each one of those building blocks essentially implements a classification test in which it outputs a conditional distribution of a label, which here is the symbol, given its input. Consequently, such building blocks can be accurately learned using classification network with softmax output layer trained to minimize the cross entropy objective. Consequently, we can implement soft iterative interference cancellation method in a data-driven manner by replacing those building blocks with dedicated classification DNNs. Now, the question that comes to mind is, how do you train the resulting architecture? And there are actually two approaches to train this resulting architecture. First, it's just train the whole thing in an end-to-end manner. Namely, we take the sum cross entropy loss, which means that we're essentially only looking at the overall output of the deep receiver. Now, by taking this approach, we're essentially using our training to jointly adapt all the parameters of the system, indicating that we are expected to need a large number of labeled samples in order to train the network. Alternatively, we could also build upon our prior knowledge of the purpose of each one of those building blocks, and we can train each one sequentially using the block-wise cross-entropy loss. Here, we're using the same training set to adapt each one of those building blocks separately. Namely, this training set is used to adapt a much smaller number of parameters, implying that the overall receiver can be trained using a smaller number of training data. Here we'll only show one numerical example. I invite you guys to attend our talk later on this week, in which we'll present a more in-depth analysis of this architecture. But what we see here, well, this is just a small scale channel, a 6x6 Gaussian channel, for which we can actually compute the minimal achievable error. This is the red curve. And the blue curve is the performance achievable using the model-based iterative soft interference cancellation method. Now, the purple curve and the green curve here are the performance achievable using the proposed architecture, whether it's trained in an end-to-end manner or trained sequentially. Now, as we can see, the performance comes quite close and even essentially coincides with the model-based algorithm, which, as we can see here, achieves relatively good performance, which is quite comparable to the minimal achievable error rate. For comparison, this is DetNet, the unfolding based, which is trained here using 100 times more samples compared to the ones we use for training DeepSeek. The performance it achieves here, this very poor performance, is what happens when it is trained using the exact same number of training sets. Furthermore, we again see that not only are we able to learn to implement interference cancellation from a small number of trainings, from a small training set, we're also obtain improved robustness to uncertainty. Again, we can plot here the curves, the dashed curves are the same model-based algorithms, but here they have inaccurate knowledge of the underlying channel. As we can see, they deteriorate significantly. For comparison, our algorithm at the DeepSeek, both with end-to-end training and with sequential training, achieves roughly the same performance as it does with accurate training, implying that by implementing the algorithm in a data-driven fashion, we're not able only to operate without prior model knowledge, we're also improving the robustness to uncertainty. Now, again, I invite you to join our presentation of this work later on this week, in which I will also show how it operates in much larger scale channels and for nonlinear channels. So far, we have developed hybrid data-driven algorithms for symbol detection, namely Viterbinet, BCG-RNet, and DeepSeek. One of their main advantages is their ability to adapt using a relatively small number of labeled samples. What we're going to show now is how this ability can be translated into the capability of tracking channels in an online manner. To that aim, we will exploit the inherent structure of digital communications, recalling that in digital communication, the bits are not purely random. For example, protocols induce structure. They imply that if we have a message conveyed from a transmitter to a receiver, what is actually transmitted over the channel is not just the message, but also header and pilots, which imply that there's a small portion of the frame which is known to the receiver and can be utilized to adapt its deep symbol detector, assuming that this deep symbol detector can be tuned using a relatively small number of training samples. Furthermore, the presence of error correction codes can only so be exploited. Error correction codes implies that if we transmit a message from a transmitter to a receiver, even if the symbols are improperly detected by the receiver, it may still be able to recover the message by utilizing the presence of error correction codes. How can error correction codes be exploited to facilitate online training? Well, what we're going to show here is that the presence of these error correction codes gives rise to semi-supervised training. To that aim, let us consider a coded communication setup as depicted here. Here, the transmitted bits are first encoded using a forward error correction code and modulated into a set of symbols transmitted over the channel. They are recovered using some pre-trained deep symbol detector into a set of symbols, which are then forwarded to decoding using a forward error correction decoder. Now, the channel may start changing in time such that at some point, we may start observing errors due to the fact that the channel with which we were trained is no longer the channel under which we are operating. So we may have some symbol detection errors. However, if the number of errors is not larger than the homing distance of the code, we should still be able to recover the bits accurately. And if we have an accurate recovery of the bits, we can re-encode them and remodulate them, generating our knowledge of what the transmitted symbols were, allowing to adapt the deep symbol detector using our knowledge of the channel output and our encoded and modulated symbols as to train in a self-supervised manner. Consequently, we are now able to track channel variations online by utilizing data combined with our prior knowledge of the inherent structure induced by error correction code to train our deep symbol detector to track channel variations online without having to provide additional artificial training. Now we will show a numerical example demonstrating how this works. we will transmit a set of Reed-Solomon block code words. Each code word corresponds to a single block, and the channel changes between blocks. Now, the block size here, this is a 255 on 2 to 3 Reed-Solomon block, means that each block corresponds to the order of only 2,000 symbols. Now, we will compare here the performance of ViturbiNet with online training, the proposed approach, and also to ViturbiNet, which is only trained once using the initial channel condition, and ViturbiNet only trained once, but using a broad set of channels. This is what we call composite training. And we will compare it to Viturbi, which operates with instantaneous channel knowledge, know the channel knowledge at each block, and Viturbi, which only knows the first channel. So let us begin. And what we are going to see here in this upper plot, this is the bit error rate of all those detectors per block. And in the lower plot, we see these are the taps of the channel and how they change. And as we can see, the taps start changing in time, and at some point they become notably different from the initial channel taps, and then we start seeing errors in the initially trained and in Viturbi with only initial channel state information. At some point, we can see that the channel is much more attenuated compared to the initial channel, and then we start seeing errors appearing, but still we are able to track the channel online using ViturbiNet. At some point, even ViturbiNet with online training exhibits some errors, but it is still capable of tracking the channel variations online, maintaining negligible bit error rate over time. And at some point, this is a periodic channel. It will return to its initial state. And then what we can see is that ViturbiNet with online training is actually able to track it all the way. Now, this is an experiment which is carried out on a laptop, on a conventional laptop. So the fact that ViturbiNet can train with a very small number of training set allows us to actually implement this in real time, because not only can we adapt using a very small number of training samples, also this training period is relatively small. To conclude this part of the talk, we emphasize that wireless communication is inherently different from conventional machine learning applications like computer vision and speech processing. First, there are established algorithms to tackle these problems, at least those of receiver designs, which we are considered here, such that optimality is achievable and actually matters. Namely, if we have a receiver which operates well on a broad range of channels, doesn't mean that it is optimal for any. Furthermore, channel conditions are dynamic, and we want to be able to track those variations online, motivating the need to first utilize architectures which do not require a large number of training samples, and the ability to exploit the inherent structure of digital communications. Now, we know that machine learning brings powerful data-driven tools which can facilitate and improve existing wireless communication algorithms. Yet, machine learning is not magic. In the end of the day, it's highly parameterized optimization, which typically requires large label dataset. As Yoda says, use it wisely. Not just plug and play, we need to understand how to use it and how to combine it with existing knowledge, taking into account its capabilities and its limitations. What we have showed here and focused this part of the tutorial on is on data-driven hybrid algorithms, which are able of improving existing communication algorithm by allowing them to operate in a data-driven fashion, such that we remove their model dependence. For example, we can now implement iterative soft interference cancellation without being restricted to linear channels. And it also robustifies these algorithms, reducing their sensitivity to uncertainty. We also shown how by exploiting the structure of digital communications like protocols and channel coding, one can train deep receivers to track channel variations in an online manner in a semi-supervised fashion without having to provide additional synthetic training. So far, we've just discussed symbol detection. There are many other areas in signal processing which are dominated by model-based algorithms, not only symbol detection in communications. Well, there are other aspects on communications, but also in radar and control and various other signal processing applications. And we conjecture that the approach of hybrid data-driven algorithms can have great potential beyond wireless communications. And essentially what we showed here, we believe, is only the tip of the iceberg in combining machine learning and model-based algorithms. The application of machine learning, and particularly of data-driven hybrid algorithms, for wireless communications gives rise to a multitude of interesting research directions. To name a few, we first note that empirically, those data-driven hybrid receivers such as Viterbinet and BCJ-RNet and DeepSeek were able to achieve their performance of their model-based counterpart for a broad range of channels using the exact same architecture, where the difference was in the samples used for training. This indicates that perhaps by utilizing machine learning, one can implement a feasible and hopefully also provable universal detector, namely a detector which is capable of achieving performance within a controllable gap from the optimal performance over a broad range of different statistical channels. Additional issues for future research are more from an applied perspective. For example, one can consider the optimization of deep receivers, like utilizing additional forms of structure inherent to coded communication, to digital communications, like frame and packet structure for online adaptation, utilizing model learning to determine the architecture, the number of layers, the number of hidden nodes in each layer to optimize the performance of deep receivers. Additional use cases can be considered. We have looked at a receiver designed for finite memory channels and for uplink MIMO channels. For downlink MIMO channels, for example, we know that successive interference cancellation combined with superposition coding can approach the capacity region of downlink NOMA systems, motivating looking into the implementation of these model-based algorithms in data-driven fashion. Finally, we can also note that the weaknesses of deep learning can have an effect on their implementation and application in wireless communication. For example, we know that deep networks are sensitive to adversarial examples. Namely, one can provide an input with a very weak level of noise, which will change the inference and decision of those deep networks considerably. This gives rise to the potential of new jamming methods designed for deep receivers, aiming to exploit their weaknesses to adversarial examples. Consequently, the combination of machine learning and wireless communication gives rise to a multitude of exciting new research directions, and we hope we have given you some pointers and intrigued you for your future research.